Hey guys, this video is about conjugates, polyprotic acids, and salts. So first, conjugates. The stronger an acid is, the weaker its conjugate base. Remember, the conjugate base of an acid is just what you get after you remove one proton, H+. And so if you have a strong acid, like nitric acid, its conjugate base is basically not basic at all. And the stronger a base is, the weaker its conjugate acid. So sodium hydroxide is a strong base, hydroxide ion, and so its conjugate acid, which would be water, is a very weak acid. So these are just some examples of a strong acid like nitric. Its conjugate is essentially not basic at all. A weak acid might be cyanic acid. Its conjugate base, after you remove a proton, you have the cyanide ion. Well, that's a relatively strong base. It's not classified as a strong base, but it's a strong weak base. And so we have a strong base like hydroxide. Its conjugate acid is water. It's a weak acid. We know about the autoionization of water. A weak base might be ammonia. It is ammonia. Ammonia is a weak base. Its conjugate acid is the ammoniumide, which is a fairly strong acid for a weak acid. It's not classified as a strong acid. All right, so strong acid, weak conjugate base, strong base, weak conjugate acid. So there's a relationship between the Ka for an acid and Kb for its conjugate base, or Kb for a base and Ka for its conjugate acid. Now we have to be careful. This only talks about the relationship between conjugates here. So if we have a weak acid, it has a Ka, and its conjugate base, after we remove a proton, it's Kb. If you multiply that Ka times the Kb, it's equal to Kw. I'll show you why in a minute. Likewise, if we have a weak base with its Kb, if we multiply that Kb times the Ka for its conjugate acid, we get Kw. So here's why. This equation here describes Ka for any weak acid, right? And there's a Ka expression. Hydronium ion concentration times the conjugate base over the acid. Likewise, this is the equation that describes Kb for a weak base. Now, notice, okay, look at this carefully, guys. The equation for the Kb is not just the reverse of the equation for the Ka. Hydronium here as opposed to water here. So those are different. But anyway, this is the equilibrium expression for a weak base, the Kb. Concentration of the conjugate acid times hydroxide over the concentration of the base. So if we take Ka times Kb, like I'm showing you up here, and we put in these expressions, so Ka here, Kab, look here, look, the concentration of the conjugate of the base cancels, the concentration of the acid cancels. What we're left with is just the concentration of hydronium times the concentration of hydroxide. Well, that's the definition of Kw. And we know Kw is 1.0 times 10 to the minus 14th at 25 Celsius, which we always assume unless we're told otherwise. If we take the log, but base 10 on both sides of this, because the log of A times B is equal to the log of A plus the log of B, we get pKa plus pKa equals 14.00. So those are useful relationships, and here we'll use them. So we're given that the Ka for nitrous acid, HNO2, is 4.5 times 10 to the minus 4th. What's Kb for its conjugate base, which would be the nitrite ion? So let's go ahead and calculate that real quick, and come on back when you get an answer. Welcome back, guys. So we use Ka times Kb equals 1.0 times 10 to the minus 14th, or because we want Kb, we rearrange this. So Kb equals Kw over Ka. Kw is 1 times 10 to the minus 14th. We were given Ka, and we get 2.2 times 10 to the minus 11th for Kb. That's all there is to that. All right, now, polyprotic acids. Polyprotic acids are acids that have more than one acidic proton. And when you have a polyprotic acid, what happens when you put that acid in solution, it loses its acidic protons successively, one after the other. In other words, the first acidic proton is lost entirely, as much as it will be anyway, and then the next one, and then the next one, and so on. So the Ka for the first acidic proton is called Ka1, and for the second one, Ka2, and if there's a third acidic proton, Ka3. So phosphoric acid has 3 acidic protons. And so this equation here describes Ka1, losing the first acidic proton, one of these, leaving behind dihydrogen phosphate. Ka is 7.5 times 10 to the minus 3. Then the next acidic proton is the second one. When we lose this is the equation that describes that. We see we've lost one of these, made another hydrogen ion. Ka2 is this number. And then the Ka3 describes losing the third proton, like this. Now notice, okay, look at this. This is what happens all the time with polyprotic acids, all of them. The difference between the size of the successive Kas is large. In this case, it's 5 orders of magnitude, so 100,000 times different between Ka2 and Ka1, and likewise between Ka3 and Ka2. What that means for us, and you'll see this in an example we're about to work out, is that the concentration of hydrogen ion in a solution of a polyprotic acid is really only depends upon the first acidic proton, and thus the pH depends upon only the first acidic proton. This proton and this proton don't add anything appreciable to the concentration of hydrogen ion in solution. They do add some, but they're usually buried within the insignificant figures. You'll see that in the example we're about to do. So here we go. So we have a polyprotic acid, oxalic acid. We call that a diprotic, by the way. 2 acidic protons. That's its formula, and there's Ka1 and Ka2. So here's the idea. We start out with a 0.259 molar solution of oxalic acid. So we make up a solution so that it's originally 0.259 molar in just oxalic acid. Then it loses its protons, or some of them anyway. We want to know the concentrations of all the species present other than water. Hydrogen ion concentration, hydrogen oxalate, and then oxalate concentrations. So why don't you guys go ahead and work that out real quick and come on back when you get an answer. And welcome back. So here we go. So the first acidic proton, so we do this successively. We do the first Ka, the first acidic proton. There's the equilibrium describing the loss of the first proton. There's the equilibrium expression, products over reactants. And from the ice table, because we start with 0 of these and 0.259 of this, we end up with x squared, Ka1 equal x squared over 0.259 minus x, and that's equal to Ka1, which is this. Notice, guys, we cannot neglect x in this equation. If we do, we get nonsense answer. And when we solve it, so I've solved this, the full quadratic, and I found that x is equal to 0.098 molar. Definitely a lot more than 5% of 0.259. Okay, so now we have x, which is going to be equal to the concentration of hydrogen ion, the concentration of hydrogen oxalate at this point, and the concentration of oxalic acid will be our original concentration minus x, because it loses 1 for every 1 hydrogen it makes. And so if you subtract x that we got here from our original concentration, we now then know the concentration of the oxalic acid in solution at that point. That's undissociated, about 0.161 molar. Okay, so that's one of the things. That's one of the species. So now at this point, the concentration of hydrogen oxalate and hydrogen ion are both equal to x, which is 0.0975 or so. Now we do our second acidic proton. So I'm gonna show the ice table for this one, and our initial concentrations will be what we got after we lost our first acidic proton. So this x goes here for the initial concentration of hydrogen oxalate, hydrogen ion, but we don't have any oxalate yet, so that's 0. And then because Q is 0, shifts to the right, minus x plus x plus x. So our equilibrium concentrations look like this. And we plug these guys into the Ka2 expression. Look at this. Look how this works. Ka2 is equal to, this is going to be x times 0.0975 plus x over 0.0975 minus x. Now, if that's equal to 6.4 times 10 to the minus 5th. It's a quadratic. We could solve it if we had to. But let's see what happens if we neglect x. Now this x we can't neglect. It's there. It's multiplying, not adding. But if we neglect x compared to 0.0975 here and here, that's gone. Notice these two numbers cancel, and we just have x is equal to Ka2. And that happens every time. And which means that x is 0.000064 molar. Was that a good assumption? Oh yes, oh yes. So this is 6 times 10 to the minus fifth. This is like 2 places down from the last sig fig in here. So that was a good assumption. And we have our X for our second acidic proton, which means we now know the concentration of the oxalate ion at equilibrium, which is just X, so 6.4 times 10 to the minus fifth molar. Now look at this, the concentration of the hydrogen oxalate and hydrogen ion, because we could neglect X compared to these numbers right here, and it's so much smaller than these numbers, at equilibrium, the concentration of hydrogen ion and hydrogen oxalate is the same as we got up here, 0.098 molar. And that's because, we lose so little of it when we lose the second acidic proton here. And then, of course, the concentration of the oxalic acid we got up here, 0.161 molar. And so if we wanted the pH, we just take the negative log base 10 of 0.098 or 0.0975. And there you go. All right, salt hydrolysis. This is cool stuff. So when you dissolve a strong electrolyte in water, so something that dissociates to a good extent, so conduct a current and all that. If the anion that you get is the conjugate base of a weak acid, or the cation is the conjugate acid of a weak base, and you'll see that in just a minute, hydrolysis occurs. What does hydrolysis mean? Hydrolysis, breaking apart water, and it affects the pH of a solution. For example, potassium fluoride. So we know from Chem 101 solubility rules that if potassium is the cation, then that ionic compound is soluble. So when we dump some potassium fluoride into water, it dissociates into potassium ions, which we don't care about now because they're not doing anything, and the fluoride ion, which it ends up, we do care about, because the fluoride is the conjugate base of hydrofluoric acid, which is a weak acid, which means this is going to be a base. And so what happens, guys, is this is hydrolysis. The fluoride ion reacts with water, okay, pulls a proton off, makes hydrofluoric acid and hydroxide. It's producing hydroxide. It's accepting a proton, however you want to look at it. It's donating a pair of electrons. It's being a base. Now, we're given that Ka, usually you're given Kas rather than Kb. So we're given the Ka for hydrofluoric acid, 7.1 times 10 to the minus fourth. Our job is to calculate the pH of this solution up here, starting with 0.159 molar potassium fluoride, which, by the way, means there's 0.159 moles per liter of the fluoride ion to start with. So this is just an equilibrium problem, ice table sort of thing. But we have to get the Kb and all that stuff first. So why don't you guys work that out and then come on back when you get your answer. Welcome back, guys. So here we go. There's the equilibrium that affects the pH of our solution, and it's acting as a base, and it's the conjugate base of hydrofluoric acid. We find Kb by taking Kaa times Kb equals Kw. Solve for Kb. Kw is 1 times 10 to the minus 14. Ka is this. And remember, we always assume the temperature is 25 Celsius unless we're told specifically otherwise. Anyway, when you plug these numbers in here, we get our Kb, 1.4 times 10 to the minus 11th. Now that we have Kb, that's our equilibrium constant for this reaction. Set up an ice table. It's pretty simple. It's just going to be at equilibrium x 0.159 minus x here. So there we go right here, equilibrium expression. And now, okay, because this is such a small number, it's probably going to be a good assumption to neglect x in this case. The reason it wasn't in that other example was that k was like 5 point something times 10 to the minus 2, much larger than 10 to the minus 11th. So let's try it. Neglect x, we get this, simple to solve. Multiply through by 0.159, take the square root, and we get x is 1.5 times 10 to the minus 6. Yes, that's definitely a lot smaller than 0.159, way less than 5%. We can neglect it. It was a good assumption. All right, so now we know x, which means that because x is equal to concentration of hydroxide and hydrofluoric acid, we want the pH of the solution. Well, we have the concentration of hydroxide, which means, there's a couple ways you can go about this, but if we know the concentration of hydroxide, what I usually do if I want the pH is I get the pOH first. Negative log base 10 of the concentration of hydroxide. When I do that, I get 5.82 or so. And then all I have to do to get the pH is to take 14 minus 5.82, and I get about 8.18 for the pH. And real quick, does that make sense? Well, yeah. We said this is going to act as a base, so we expect the pH to be higher than 7, and it is. So it's not like an extremely basic solution, but it's definitely basic. It would feel slippery to you if you put your hands in it, because bases feel slippery and taste bitter. Acids are sour. So metal cations, this is cool stuff too, guys. A metal cation can also react with water and affect the pH of a solution, but only small metal cations that are highly charged, such as aluminum, chromium-3, iron-3, bismuth, and beryllium. These guys have a +3 charge, which is highly charged. This is pretty highly charged, +2, but it's really small, but that helps it out. And so what happens is we get the water molecules associating with these ions through ion-dipole interactions, intermolecular forces. So it looks something like this. This would be the aluminum ion. So I'm talking about aluminum. I just picked aluminum for an example. So this would be the aluminum ion, and it ends up, and there's no way you'd know this ahead of time, but it ends up with this one, you get an octahedral geometry about this. We get 6 water molecules. So there's aluminum, the red circle is supposed to be the oxygen atom, and the white circles are supposed to be the hydrogens. I don't know how good it came out, but there it is. So we have 6 water molecules attracted to this aluminum ion through ion-dipole interactions. So the +3 charge here attracts the lone pairs of electrons on the oxygen atoms, and we have this structure here. Formula would look like this: AlH2O6 overall +3 charge. What happens is, in solution, because this aluminum ion is pulling electrons towards it, because it has a +3 charge, which is really high, through this ion-dipole interaction, it's pulling electrons away from the oxygen-hydrogen bonds here. And so when another water molecule that's not associated with an aluminum ion bumps up into this one of these hydrogens is already kind of loose. It's kind of, shaky out there. And so this lone pairs of electrons are attracted to the positive charge, hydrogen bonding basically, but it pulls off this hydrogen, and we make the hydronium ion over here, leaving behind this, it's not an anion, it has a +2 charge instead of a +3. Looks like this. So formula-wise, it looks like this down here. So this is the hydrate of aluminum plus water. And what's over here is we had 6 waters here. We lost a hydrogen ion off of one of those. So we have 5 waters left and OH, right? And because this has a negative charge, +3, we have an overall +2 charge and hydronium ion. And the Ka, so we're basically making hydrogen ion or hydronium ion. So this is being an acid, right? It's accepting electrons, donating a proton, however you look at it. Ka is 1.3 times 10 to the -5. That's not terribly small. That's that's a decent size Ka. It's going to affect the pH of this solution just by having a metal ion in there. I think that's just cool. All right, salt solutions. So what we just saw, that only applies, guys, to small, highly charged metal ions. If they're big, larger, or not highly charged, then that doesn't happen. That's hydrolysis also. So that means that the group 1A and 2A metals, alkaline earth metals, do not do this, except for beryllium, which is always a kind of a weird one, because beryllium has a +2 charge and it's small, it hydrolyzes. Now, we said this before, if we have an anion that's a conjugate base of a strong acid, then no hydrolysis. But if both the cation and the anion hydrolyze, so again, by hydrolysis, I mean reacting with water and making it either acidic or basic. We saw with the fluoride ion, the hydrolysis where it produced hydroxide. We just saw with the aluminum ion, with hydrolysis, it produced the hydronium ion. If both the cation and the anion hydrolyze, so let's say we put some aluminum fluoride into water, what's going to happen? It's going to be acidic, or is it going to be basic? Well, it depends. I forget. It depends which has the higher Ka. But anyway, if the Ka is greater than Kb, the solution will end up being acidic, and that means that the metal ion overpowers a little bit the anion. But if Kb is greater than Kw, the opposite is true. The solution is going to be basic, right? And if Ka is about equal to Kb, then we have a pretty close to neutral solution. So oxides and hydroxides. So oxides are metal oxides. are, O2 minus ion. So, for example, sodium oxide, and, calcium oxide, and alkaline earth metal hydroxide. So, calcium hydroxide, barium hydroxide, strontium hydroxide, like that, are basic. And here's why. Except for, again, beryllium is always the outlier. Beryllium oxide is amphoteric, meaning it has both acidic and basic properties. Which one it exhibits depends upon its environment. So, for example, metal oxide. Sodium oxide reacts with water and makes sodium hydroxide, which is basically produces hydroxide ion. It's basic. Calcium oxide, alkaline earth metal reacting with water, makes calcium hydroxide, which again is basic. The last thing here, guys, non-metal oxides. So carbon dioxide, sulfur trioxide, etc. If the non-metal has a high oxidation number, then solutions of these non-metal oxides will be acidic. And here's how that happens. Carbon dioxide. So the oxidation state for carbon here is +4. That's pretty high. Reacts with water and makes carbonic acid. Right? It's an acidic solution that results. There's other things that goes on with this. This dissociates, makes carbon dioxide and water. It goes back the other way, but it does affect the acidity. Sulfur trioxide reacts with water, makes sulfuric acid. Acid rain, right? That's acid rain right there. Dinitrogen pentoxide reacts with water, makes nitric acid. Tetraphosphorus dicoxide reacts with water, makes phosphoric acid. And dichlorine heptoxide reacts with water, makes perchloric acid. And that's all there is to that, guys.